So we proved yesterday that if you had a closed form and you pulled it back by homotopic maps, you got the same integral. Integrating over compact orientable, blah, 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 blah. So I want to show you today a whole pile of applications of that. So the theorem we proved yesterday, we had X compact oriented k-dimensional manifold. We had F and G mapping X to Y homotopic. So remember, that means that you had this smooth function that had a time parameter in it, and as the movie ran from time 0 to time 1, you went from map F to map G. And omega was a K form on Y that was closed. Then what we proved by Stokes' theorem was that integrating the pullback of omega on X was the same as integrating the pullback by G of omega.
Can the function, like the big F that does the homotopy, can it cross itself?
Sure.
Okay.
All it has to do is be smooth, but yeah, it doesn't have to. Right there. If you go on and study more topology, you'll learn more restrictive notions besides homotopic, which come into questions about, for each time t, do you have a particularly well-behaved map? And there are other restrictions. Okay, so I want to do applications of this. The first thing I want to point out is a definition here is X, let's say M, is simply connected. I don't think I've mentioned that word before. Right. So simple connectivity basically says that any closed curve in your space can be shrunk to a point in a continuous way. In other words, can be homotoped to a constant function. So M is simply connected if every F from a circle into M, so this is a mapping from a circle to M is just going to be a closed curve in M. Right? That's what we talked about yesterday. A circle just gives you a closed loop in your M. If every F is homotopic to a constant map, what does a constant map do? Constant map just sits, doesn't go anywhere. So what am I saying? I'm saying simply connected means if I take any closed curve, I have a way of squishing it to just sitting at a point. So this is what you would see at time 0. This is what you would see at time 1. And in between, you could imagine the curve deforming gradually, getting smaller and smaller and smaller. So, for example, a ball is simply connected. So, e.g., any convex set is simply connected. Or any star-shaped region, I think I mentioned that to you guys earlier, is simply connected. You have a convex set, you pick a point, then any curve you take, you can shrink by taking straight lines to your center point. So at time a half, you're halfway. So I could even write a formula for that if I were in Rn, for example, take f of x t, and I'm going to join that point to a point x naught. I'm going to take, at time 0, I want to have x. time 1 I want to have x naught, then this map takes every point and joins it by line segments to the point x naught. As t runs from 0 to 1, the point travels along that line segment.
Is it necessary that at t equals 1/2, the point's halfway there? Or would
It's not necessary, but it's happening when I'm doing this. No, it's certainly not necessary. So, give me a space or a manifold that is not simply connected. A ring, a torus, a circle. A circle is not simply connected. So, not simply connected.
Is it this simply connected?
Yes, because it fits this. A circle itself, R2 minus the origin, is not simply connected. A torus is not simply connected. Because I can prove it to you immediately with this. If going around once around the circle were homotopic to just sitting at a point, integrating our famous 1 form would be equal to integrating 0. Because sitting at a point, the integral is 0. So if the circle were simply connected, the loop that goes once around would have the same integral with our famous 1 form as the constant map. Well, a constant map pulling back gives you 0. So you have 2 pi equals 0. So this differential form stuff is very good for proving things are not homotopic. So, in fact, so using this idea now, you can get a corollary, which I told you guys way back earlier in the chapter. If M is simply connected, any closed 1 form is exact. See how you might prove that using this? What did we prove was a sufficient condition for a closed form to be exact? Not on the region, necessarily, but what was the following are equivalent? Closed 1 forms that were exact 1 forms correspond to conservative forces. And what detects whether you have a conservative force or an exact 1 form? Integrals have to be path independent. Or omega is exact if and only if the integral of omega over C is 0 for all closed curve C. Well, but if you're simply connected, any closed curve is homotopic to a constant map. So by simple connectivity, for any map of the circle with image the curve C, so you have a closed curve, you think of it as a mapping from the circle to your space that traces out your curve. Then we get the integral of omega over C is the integral of the pullback of omega to the circle. So you just parameterized your curve by this mapping. Pulling back omega, you get the same thing you would get integrating omega over the curve, but by simple conductivity, this is equal to the integral of G pullback, which is a constant map, and that's 0. take a constant map and pull back any differential form, you get 0. So for any closed curve C, the integral is 0. So by what we proved in section 8.3, omega is exact. So there's a, would you accept that as an application, Wyatt? Okay. Grudging.
Are they all a circle? I mean, double circle.
Any closed curve is a map, can be represented as the image of a map from the circle to n. You parameterize the closed curve from 0 to 2 pi, but you think of the circle as going around 0 to 2 pi.
We could have non-convex sets, that was something.
Oh, absolutely. Oh yeah, absolutely. R3 minus a point is simply connected.
Yeah, R2 minus
No, R2 minus a point is not.
So R4 is.
R4 minus a line is simply connected,
What, minus a point?
for sure.
Okay.
Yeah, once you're higher dimension than 2, pulling out a point does not destroy simple connectivity. It makes for a more interesting topology, but it's not simple. It is still simply
So
connected.
you go minus a line is not simple connected.
R,
R3 minus a line.
no, that's right.
So it's as we go.
So, wait, following that logic, is R5 minus the planes connected?
Yes.
So all you need is is essentially a projection of a plane that's connected. So if you could have like a two-dimensional manifold that is connected along that line.
I'm not following. I'm not following what you're saying. I mean, this is, I'm giving you examples. I'm not saying anything like being necessary conditions.
Why is R two minus the origin not super?
Because this loop is not homotopic to a constant. We proved that. I mean, that's what our integral being 2 pi tells us. Okay, so as an application of this flavor stuff, I want to talk about the fundamental theorem of algebra, and then we're going to talk about the Hairy Ball theorem. So, it's quite surprising, actually, that there were very many flawed proofs of the fundamental theorem of algebra running around for centuries, and it really took Gauss, who was thinking about topology, in effect, to give the first rigorous proof of it. And it is almost impossible. This is for public consumption, so I have to be very careful what I say. I do not know of a I do not know of a proof of the fundamental theorem of algebra that is completely devoid of calculus analysis topology. The most algebraic proof I know still needs to know that a real polynomial of odd degree has a real root. And to prove that, you need the intermediate value theorem. So it's actually, for those of you who don't remember what the fundamental theorem of algebra is, it says let P be a complex polynomial with complex coefficients. So that means you can write it in the form of numbers times powers of your variable, where the coefficients here are all complex numbers. And the stipulation here is that the degree of the polynomial that you're used to from algebra is the highest non-zero coefficient that appears. So the fundamental theorem of algebra says, so we say the degree of P is n when the a sub n is not 0. So you write it out, no higher powers appear, and you make sure that the highest power that I've written down really appears. And then that's the degree of the polynomial. And the theorem of the fundamental theorem says a polynomial of degree n has n roots, counting multiplicities. So you guys know examples of real polynomials don't have any real roots at all. X squared plus 1, for example. And the complex numbers are made up exactly so that the polynomial x squared plus 1 now has two roots, and they're called I and negative I. So you'll learn more about this when you take Math 4000. All right, so I want to actually give you a proof of this based on all the stuff we've been doing with homotopy and Stokes theorem. Okay. So by the way, the standard proof, and I'll just do the standard proof as well here, although I want to say a bit more, is that you show it has one root and then you do an induction argument. So once you get a root, you can divide through by z minus that root and you get a polynomial of lower degree, so you get a proof by induction. Everybody okay with that? So the usual flavor, but I'm actually going to do a bit more, although I'm going to run past my 50 minutes today. But the usual flavor is use induction, and show one root. So if you find a root, then by induction we reduce to a polynomial of one degree, which by induction hypothesis has n minus 1 roots. Now you have to start your induction with a linear polynomial. It's not too hard to find a root.
Have a sub j as an element of
Complex numbers.
Script C.
No, I think to see with the line through it.
Hmm? What?
We were discussing how it looks like.
Oh. It's like the R's that I've been using all along with an extra line in it. All right, so here's the idea. If it had no roots, so we're going to use our universal one form, our ubiquitous one form, which is defined where?
R2 minus 2.
Everywhere in the plane except the origin. So this is a one form on all of R2 except the origin. And I'm now going to say that that's what the complex numbers form is in R2. So is there anybody who's actually never seen complex numbers at all? So you know that you can think of complex numbers as things of the form real number plus real number times I, and that's a copy of the plane. So C I'm thinking of as R2, where the complex number A plus BI corresponds to the vector AB. And we're actually going to come back and do a bit more with complex numbers when we get back to linear algebra at the end of the course. So I'm going to use my omega. All right. Suppose my polynomial P has no roots at all. Then that means that the polynomial maps all the complex plane, all z's that are complex numbers, to a non-zero complex number. Right? Fair enough? Now, for any radius r, consider the d sub r, which is the closed ball of radius r. So look at the disk of radius r centered at the origin.
What is What is the absolute value?
So that's the same thing as length of a vector, except that with complex numbers, people write a single absolute value sign like they do for real numbers. That's just the way people write with complexes, so I'm using the same notation. It means the same thing as magnitude as a vector. Okay. So what would have to be true if I took the pullback of my omega and integrated over the boundary of the disk?
Well, we could use Stokes' theorem.
We could in fact use Stokes' theorem, and we would get the integral over the disk of the d of the pullback.
Pullback is
Yeah,
zero.
You're catching on, aren't you?
A little bit.
So that's pullback of d omega, which, as everybody knows, is 0. So the integral of 0 is 0. So we would get the integral of omega around every circle of radius r would have to be 0, if this were true. So notice I'm using Stokes' theorem as Daniel suggested, but I need to know that the pullback is a smooth form everywhere, and it is because my p doesn't hit 0. So everything is hunky-dory. All right, but I'm going to show you, using homotopy, that this ain't 0. So we'll have a contradiction, and everybody will be happy. All right? So here's what I want you to think about. Think back to your intuitive calculus days. What does P of Z look like when Z is large? So think about polynomials. What dominates the behavior of a polynomial when you're far away from the origin?
In.
The greatest degree.
If it's positive or negative.
Well, okay, we're doing complex stuff now, so you don't get to say positive or negative, but you're right. When you thought about graphing real polynomials, behavior at infinity was determined by the leading coefficient and whether the power is even or odd. But do you agree that I ought to be able to make some argument that that polynomial looks a lot like the leading term? What does looks a lot like mean?
The ratio of them as Z approaches infinity is 1.
Okay. Or you could say the limit, which is what Daniel's actually saying. But here's what I'm going to say. As Z goes to infinity, if I take the stuff below the leading term, and I look at its ratio to Z to the nth, that limit is 0. So in other words, this means, e.g., for large enough R, when the magnitude of Z is R, I can say this numerator divided by the magnitude of the denominator is less than a half. Right? That's just limit being 0. So for large enough r's, I'm within epsilon equals a half of the limit. Okay? So here's what I'm going to do, folks. I'm going to write down a homotopy between so I'm going to write down, here's what I'm going to do. I'm going to take Z to the nth, I guess I'll put the AN there. The AN is really irrelevant. degree I could factor out an a sub. All right, I'll leave the a n. I'm going to put the a n here. Yeah, if I'm doing that. Okay. I should have said we can assume a n is 1 from the very beginning, but I didn't do it. So here's a n, z to the n, and here is p of z, the whole polynomial. What I want to make sure here is that when I draw the line segment joining them, that I don't go through the origin. If I can be sure that the line segment joining these two points in the plane doesn't go through the origin, then I will have a homotopy between this function and this function that doesn't go through the origin. So it will be a homotopy of maps to C minus the origin. Does everybody agree with that? So let's see. T equals 1. At t equals 0, I want to have my regular polynomial. And at t equals 1, I have just a n z to the n. So p of z, z0 is p of z, little p of z, and p of z1 is just my leading term. And I'm asking you the question, if I interpolate between time 1 and time 0, do I ever go through the origin? Could could capital P of zt equal 0 for some z with magnitude r and some t between 0 and 1?
Why equal of less than r?
You'll see. Good question, but you'll see. Could it happen that this line segment went through the origin? How would that, what would have to happen for that to be the case? No. When, if I have 2 points in the plane, when does it happen that the line joining them goes through the origin? They have to be opposite each other, right?
So you reflected over a line.
They don't have to be, right? So one of them has to be on the negative side of the origin from the other, literally. So what would that mean would have to be true?
It's larger than r.
The differences of their real parts.
Well, I don't want to do real parts, I don't think. I want to think of them as vectors in the plane.
So then the differences of their
Could this hold and have it happen? If what I'm adding to the a n z to the n has magnitude less than half the magnitude of this, could it end up over there when I add the two?
No.
Could I add this with this and end up on the opposite side? It can't happen, right? Because what I'm adding has magnitude at most half of the original. And if I multiply it by a factor that's between 0 and 1, it's even shorter. So for these to give 0, this thing would have to have a magnitude at least equal to the magnitude of that. Agreed? It doesn't. It's got magnitude less than half. So the answer is no. Think magnitudes of vectors. All right, well then I'm done. This homotopy takes my original polynomial and homotops it to the polynomial that's just some number times e to the nth. So the real question is going to be, for the function g of z equals z to the nth, forget the silly constant, it's some non-zero number. what is the integral over the boundary of the ball of radius r of the pullback of omega? No,
Well, we can use the homotopy thing, right?
I've used the well, no, but I'm going to say by the homotopy thing, this integral is going to equal that.
Okay.
And I want to see it's explicitly not 0. Well, what does z to the nth do? So if you're on the circle of radius r, you can parameterize it this way. Remember, I is just like putting in the second coordinate. And a fact from algebra that I'm not going to stop to do now, but I'll prove it to you later in the course. Fact to be proved later, which Haley can do for all of you, is that if you take the nth power of z, you get the nth power of r times the nth power of cosine t plus I sine t. And the cool thing is that that's cosine nt plus I sine nt. So when you multiply powers of z, you're wrapping around faster and faster around the circle. And the circle's got a bigger radius. So as you make one revolution around the unit circle, taking the nth power goes around n times. How many of you have seen this before, besides Haley? It's related to, we can get it from Euler's theorem. This is called de Moivre's formula. It's a simple case of de Moivre's formula. Do you see where we're headed? What happens if you pull back omega by this parameterization that goes around n times? What happens if you go around the circle once? What happens if you go around it n times? Alright, so the integral of g star omega by explicit computation, which I'm going to skip, but you can do it, is going to be 2 pi times n because of this. Well, let's see. By homotopy, we're supposed to get the same integral. Not true. N is bigger than or equal to 1. So we do not have equality, even though we have homotopic maps. What's the resolution of this problem?
P has to have roots.
P has to have a root. So this contradiction tells you P must have a root.
I'm not responsible for proof, are
What proof?
I,
Using homotopy?
Sure.
is this the proof or the idea of proof?
Well, this is actually a proof. Thank you for correcting me. Now, in fact, so here is where I'm not going to go through all the details because I don't want to hold you guys infinitely long today. But I do want to make this comment because I can't resist it. The proof actually shows you that you can count roots, a la Gauss's theorem, Gauss's law that we've been doing for the physics. So there's a Gauss's law in the plane that comes from our famous omega. That's analogous to the Gauss's law we've been doing in 3 space using our 2 form. And it's just basically saying winding numbers, right? If you wind, so Gauss's law can be phrased this way in the plane. If you take a curve and you apply some function to the curve, you get a curve in the plane. Say it looked like that.
It was have the same quantity number?
Same as what?
The circle.
Well, no. So here's what I'm going to state is true. If f is a polynomial, and there's lots of generalizations of this, but if f is a polynomial, the number of roots of f inside gamma is equal to the winding number of the curve capital Gamma, which is what you get when you do f under gamma. So this curve that I drew winds around how many times? Winding number around 0. Winds around 2 times. So that tells you that there had to be 2 roots of the polynomial inside gamma. Do you see why it's like Gauss's law? You're integrating omega over capital Gamma, and you're counting how many times 0 is inside the curve, and that's counting 2 pi times the number of zeros inside here. All right, so what's the idea? If you had a root that would mean you'd have a point there that went to 0 here. If you took a teeny little circle around that root, what would it do? Well, it would do some curve that goes once around there, assuming this is a simple root, not a root of higher multiplicity. If this had a root of higher multiplicity, you'd go around a couple of times. That's all coming from this analysis that we did here. So here's what makes it work. And I'm not going through this to give you enough details. There's more in the book. But here's why it works. Where is this silly one form coming from? I never really told you, except that we saw it was related to d theta in polar coordinates. Yeah, we actually showed that it was related to, that it was d theta. But look at this. Now that we're thinking about complex numbers, look at that. So z is x plus iy, and just do our differential forms allowing yourself to have complex numbers. What do you get? Well, dz over z is dx plus I dy. And now I have to divide by x plus iy. Now, do you guys remember basics? I don't know, again, how much you know about complex numbers, but what's the basic way to rationalize that denominator and get rid of the I? Multiply by the conjugate. What do you get in the denominator? x squared
Plus y.
minus I squared y squared.
X squared plus y squared.
Interesting.
I'm assuming negative y, yeah.
Now let's look at what we got in the numerator. What's the real part with no i's in it? Well, we've got an x dx plus y dy. And then what's the I part? Minus how many dx's?
Y axis
Yeah,
plus y.
looks familiar, doesn't it?
Plus y.
X dy.
Sorry.
So the imaginary part of this is our famous omega. Now here's where Gauss's law comes from. Suppose you took the product of two functions and you pulled back dz over z. So I'm thinking about factoring a polynomial, so I'm thinking about breaking it into a product. How do I pull back dz? Well, it's d of fg. Substitute z equals fg, and then I divide by z, which is fg. Product rule me on the numerator. I get g df plus f dg over fg.
Equals df over f plus dg of g.
What does this remind you of? What turns products into sums?
Natural log.
Log. Does d blah over blah remind you of log?
Uh-huh.
So it's not all coincidence, right? This is like derivative of log. And log of a product is sum of the logs. What does this tell you? This tells you that if you multiply two functions, the integrals of, when you pull back omega, are going to be the sum of the two integrals. So that's going to tell you that the winding number of the product is the sum of the winding numbers. So for each root that you have inside, you're going to pick up one more winding number. Imagine factoring out root by root. So this is going to tell you the Gauss's law holds. You're going to count roots by doing this anyway. Okay, so if this starts to tantalize you, I would suggest that in the future you think about two courses. One is differential topology. By the way, I'm not done yet. I'm going to show you more differential topology. And complex analysis. So complex analysis is doing all the calculus that's built on integrals of this type. If we have, by some miracle, a spare day at the end of the semester, I'll actually talk more about that. I'm not even giving you any homework on this stuff, so I will not put this on the test. That does not apply to this other stuff we're doing, though, on which you do have homework. All right, so I want to end the topology exploration with what is arguably one of the coolest theorems in basic math.
Basic math.
And this is basic math.
And this is the Harry-Ball theorem. So the Harry-Ball theorem says you can't comb the hairs on a ball in even dimensions. Of course, it's a hairy ball, or there wouldn't be hairs to comb. So,
What is the density of the hair?
oh, it's a mathematical bunch of hairs. It's not my hair. So, first definition that you need is a tangent vector field on the sphere is a smooth function V, which assigns to each point of the sphere a vector in the space it's living in. So remember, the sphere is living in Rk plus 1. But I want to say it's tangent to the sphere. So it's a smooth function with the property that at each point of the sphere, that vector is tangent to the sphere at the point x. And so since this scares you, I'm just going to say it's orthogonal to x. Remember, the tangent plane to a sphere has its normal vector given by the position vector. So this is a much more concrete way. And the theorem is when k is even, when you're on an even dimensional sphere, like the sphere in R3 or the sphere in R4, sphere in R5, sphere in R7, when k is even, every tangent vector field on Sk must vanish somewhere. So if you think about my having unit length hairs at every point on the boundary of my head, which is the two-sphere, combing them would mean making every hair be lie-down tangent to the sphere. And I'm saying I can't comb it. Meaning there's at least one point where the hair has to go out normal to the sphere. It can't be you can't lay it down in tangent. So I think Daniel said there had to be a cowlick on the hairy ball. Pretty amazing theorem. And it was what you guys might be puzzled about unless you've been thinking about things that like some of the homework. Where is even being used? Okay, so I'm gonna fit this in without running over too much. So here, it's a really cool idea. And it's coming back to homotopy again. All right, so what are we going to do the proof? Of course, we're going to do a proof by contradiction. So suppose we have a nowhere vanishing vector field on an even sphere nowhere vanishing. Then without loss of generality, I can normalize my vectors and make them all length 1. Do you agree with that? So then we may as well assume that the length of all the vectors are 1. So I've got a unit length vector field everywhere in the sphere, and it's never 0, obviously. All right, here's the idea. At each point, you have a unit length 1 vector that's tangent to the sphere at the point x. Agreed? At each point, so at every x, oops, I don't want to do that in red. At every point, I have a v that's tangent at that point x. I'm going to now define a homotopy between f of x, which I will now write with vector symbol, the identity function, f of x equals x, and the function g of x equals negative x. So g of x, if this is the x, g of it is back behind the sphere over there. These are usually called antipodal points. So if this is x prime here, then g of x prime would be back behind the sphere. Now I want to deform, I want to give a homotopy. I want to give you a movie that starts with every x at x and runs for time 1 and ends me up at minus x. Do you see how I can do that? No, I have to stay on the sphere. So what I want to do, sorry, yes, I didn't make this clear. F and G are both mapping the sphere to itself. So the homotopy has to map the sphere to the sphere with the time parameter. So what are you saying, Patrick?
Rotate around the
But
sphere.
you have to rotate around an axis. Like that is.
Well, how do I rotate x to minus x? Do I have a good way to do it?
You can't do without
You can do
the
that
sphere.
for one.
No, I
Go
can't.
Direction B of x. You can
There
do
you
it
go.
first.
Yeah, so Patrick's got it. Follow the great circle. I can make it a yellow brick circle for you even. Follow the great circle that goes in the direction of v. Follow that great circle from x to its opposite point. So how am I using v? Well, it's telling me which great circle to follow. And what do I do for time t? Well, time t I go that fraction of the way along that great circle. I'm going to write down a formula. Here's the formula. Cosine pi t x plus sine pi t v of x. No one can argue that it's not smooth. Did I say that right? I'm not sure. Does it map the sphere to itself? Well, what's the magnitude of this vector for any t? 1, because these are unit vectors that are orthogonal. So I'm using that magnitude x and magnitude v of x are both 1, and that they're orthogonal. That tells me that the magnitude of f of xt is always 1. Times 0, you can't argue with me, I'm at x. Cosine of 0 is 1, sine of 0 is 0. What about time 1? I'm at g of x. I'm at negative x, and in between I'm rotating around this arc of my great circle. We're almost at the end of the proof. What do you think is going to be the case? If I have a homotopy here, what do you think I want to use to finish the proof to get some contradiction? We're on a k-sphere. We want to use our homotopy fact yet again. Can you think of a k-form on the k-sphere that we know something about in terms of integrals?
Volume form, which is always positive.
The thing we wrote down yesterday. Take omega, as we did yesterday, and I remind you what the formula was. It looked like this. It was built analogously to our famous area 2 form in R3. Okay? What did we say about this form? Well, we said that the integral of omega was some positive number if you integrate over the k-sphere. Okie dokie. By our humble proposition, f and g are homotopic. Therefore, pulling back omega and integrating equals pulling back g and integrating. Pulling back by g and integrating. Because omega is a closed form. Well, The integral of f pullback, what's f? It'd be the identity function. So what do you get? When you pull back by f, it's just the integral of omega. Now, what happens when you pull back by g? Well, let's see. What is the pullback of omega by g? Sorry, this stuff is not
This is
racing.
where they even.
Count minuses. If you put it in minus everywhere, you get a minus here, a minus here, a minus here, a minus here, a minus. How many minuses are there when you pull back by g?
N+1.
Oh, I'm sorry. I shouldn't have an n. That's my fault. We're in k, the k sphere in k plus 1, so the n should have been k plus 1. Right? We're in n dimensions where n is k plus 1. How many minuses are there? One for each slot, because this guy is replacing this. Do you see it? Cameron, you got it? What's the integral of the pullback by g? Well, it's minus 1 to the k plus 1 times the integral of omega. Well, what's the problem here?
They have to be equal, they're not always equal if it's an even function.
If k is even, these are opposites of each other, contradiction. If k is odd, no contradiction, and in fact, there are ways to comb the hairy balls in odd dimensions. Right, circle is obvious, and you can generalize that to any odd. So this is the contradiction when k is even. End of proof. You cannot comb the hairs.
So on the first line of the proof, when you're talking about b, that says smooth b.
Mm-hmm.
Okay.
Yeah. Yeah, my definition make it was true.
I see.
Okay. Very cool. So I hope you, A, appreciate the power of the stuff we've been doing, and B, are a little tantalized to go learn some more math. Tomorrow, we start linear algebra again.
Ooh,
I'm
thank
not
God.
excited for that,